Hello and welcome to a coding challenge. Today I'm going to attempt to make a double pendulum simulation. Now, I actually don't have a coding challenge that's a single pendulum, so I should double back and make the single pendulum challenge. I do have some videos about pendulum simulations in my Nature of Code playlist, which I will refer you to. But I really always wanted to make the double pendulum because it's like this crazy, it creates a double pendulum, which if you haven't figured out already, is having a pendulum attached to another pendulum. As you swing a double pendulum and you trace the path of the bottom point, it makes these beautiful, chaotic, kind of insane patterns. And you can see an image of it here from some other YouTube video that you could probably go and find and watch. So this has been on the coding challenge list since June 24th, 2016. And most recently I looked at it back in December and I found this wonderful reference. And so, oh, look at this. Is this the reference I wanted to look at? Yeah. So we can actually just, let's look at this here. I want to make this. Okay, so this is what I want to make. I knew right there. There's the double pendulum. So, but really what I need is the formulas on this page. So let's establish for ourselves this diagram. So what I need for a double pendulum is this I'm going to consider to be 0.00. Then this I'm going to consider to be point x1, y1. And this here, and let me be more thoughtful about how I draw these lines. This here, I'm going to consider to be point x2, y2. So there are important variables here. Well, there's a bunch of things. In theory, there are two what you might call bobs. The bob being this thing at the end of a pendulum. So there's the mass of this one, which is mass 1. There's the mass of this one, which is mass 2. Okay. I also need to keep track of this length, arm length, the arm of the pendulum. So I'm going to call this one R1 and R2. Now I just realized that if you look at the webpage I'm looking at, they called it L1 and L2, but I'm going to call it R1 because variable named L in code, it looks like a 1. It's very confusing. So R1 and R2. Then what's really important is I have two angles. I have this angle here, theta 1. And then now what's the best way for me? I think, so let me draw it. I want to be able to see that angle. So let me draw it out like this. So this being theta 2. Now this is x2, y2. And this is r2. And this is m2. Okay, I think I've got this pretty much right. These are all the variables of my system. The only thing that I really need to keep track of is theta 1 and theta 2, r1 and r2. I'm going to be calculating where these points are based on those angles. Okay, so this is the diagram. So that means, I'm going to do this in processing. That means I can start by having, I might have been backwards about the theta 2 angle, but no, it's fine. I'm good. We'll find out if we made a mistake later. So I'm going to say I need R1 is going to be 100. Oh, I forgot I was in processing. R1 is 100. R2 is also 100. Let's just have mass 1 be 10. I'm making these up. Mass 2 be 10. You know, there's also, I have the length of mass and I need this point 0, 0. So I'm going to need, okay, so then I need setup. Then I need draw. And I'm going to create a window that is, let's make it 600 by 600. And I'm going to say background 0. And then stroke, actually let's make it background 255. Stroke 0. Let's make everything a little bit thicker so we can see it. Stroke weight 2. And now, what do I need to do? Let's run this. The first thing I want to do, and I think I'm going to move this over a little bit here. The first thing that I want to do is I want the 0, 0 point to be like here in the middle. So the way to do that is I'm just going to use translate. So I'm going to say translate to 300, 50. And then what I need to do is I need to calculate x1 and x2. So x1 equals, we just need a little trigonometry, right? So how do I get to this point? How do I get to this point? Well, I need to know what's my y offset and what's my x offset. And you might realize, now this is a little bit weird, it's a little bit of a different scenario because x is actually across from the angle. Sine of that angle, theta 1, equals x divided by r1. So x actually equals r1 times sine of theta 1. Okay, so now I can calculate x1 equals r1 times, what did I say? Sine of, oh, I don't have the angle. So let me create two variables. A1 is 0, A2, angle 1 and angle 2. Sine of A1. Y1 equals R1 times cosine of A1. It's a little bit backwards than what you might see in a lot of other polar to Cartesian videos. And then I'm going to say line from 0, 0, x1, y1, and then I'll draw a nice little ellipse there. x1, y1, 16, 16. And you know, I have this mass. So I probably should actually draw it relative to the mass. So let's draw it, like, just call it M1. And then let's make sure I say fill 0. Let's run this. There we go. So we can see this is the top of the pendulum. And let's make it a little bit longer and a little bit bigger. Okay, so that's good. That's the top of the pendulum. That looks right. Now, what I need to do is calculate x2, which is r2 times sine of a2. The same exact math is going to apply. r2 times cosine of a2, but it's offset from x1, right? Oh, y1, x1, y1, right? Because this is going to get calculated according to this angle in the same way, but the offsets, the y offset and the x offset, are relative to x1, y1. So I could use translators and rotate, but I'm just going to add the offset in there. And now, to render that, I should be able to say line. Now I want the line to go to, I'm going to be like so anal retentive about this. I want to start with x1, y1, x2, y2, and then draw that next ellipse. And we should see, there we go. So this is looking good. Now let's just see, am I crazy? Is this right? So like, for example, there's no animation happening yet, but if I were to say something like, you know, pi divided by 2, that's 90 degrees. Yeah, okay, so that's right. And if I were to say like pi divided by 8 and pi divided by 4, that makes sense, right? So the angle and the length is what's controlling where everything is positioned. And I could start doing weird stuff. Like I could just say, like for no reason, like A1 plus equal 0.1. And you can see it's doing that. So in some ways I have, but this is not the actual formulas for the mechanics of how a double pendulum. Now, interestingly enough, this is an interesting sketch just on its own. Because now I could have that go the other way, and we could see, you know, what's going on here. So one thing I want to add to this, just while we're here, let me add the tracing Let me add the tracing of the path. And I'm going to do this in a kind of funny way. I'm going to create a P graphics object. And I'm going to call it canvas. I kind of don't want to call it canvas because when I make the P5 JS version of this, I don't want it to be canvas, but I'm going to do that anyway. So I'm going to say canvas equals create graphics 600 to 600. And then I'm going to say inside draw, I'm going to say canvas.begin. I'm going to do this at the end. What I want to do basically, and then I'm going to draw the background. Oh, canvas.begin draw. So this is an off-screen graphics context. It's the same as the thing that you're seeing in the window. But the reason why I want to use it is because I want to draw the background on it only once. So I can have nice trails. And then what I'm going to do is at the end here, I probably should have waited this till later. I don't know why I'm doing this now, but it's the order that I'm doing it in. I'm going to draw just a point at, I need to translate, canvas.translate. I need to do that same translation, 350. So 300, 50, and draw a point at x2, y2. So I'll make it a line or something later, but I just want to see. OK, and now if at the beginning I actually draw that as the background, image, canvas, 0, 0, canvas dot stroke weight 4, canvas dot stroke 0. There we go. So you can see this pattern that it's doing, this kind of like, is very similar to like the polar rose stuff. Because really what we have is just some oscillating going on. But I want it to be an actual double pendulum. So not just some arbitrary angle changing. OK, now, so what's interesting that's going on here? This is actually A1 is changing by a value. Remember this? I don't know if you remember this, but if you've watched any of my other videos, I've kind of got these physics engines in a lot of places. The position changes by the velocity. The velocity changes by the acceleration. There's this concept of a derivative. The change in position over time is the velocity. The change in velocity over time is the acceleration. Or I could say A1, so I could say something like A1 velocity is 0.1. Oh, wait, let me declare some more variables. So I want an A1 velocity to be 0, and I want an A2 velocity to be 0. Then I also want to have A1 acceleration and have those be 0 as well. So there, we'll see the notation on that page for a second. So this is what I want to do. I really want to have A1 change by A1 velocity, A2 change by A2 velocity, and then I also want to have A1 velocity change by A1 acceleration, A2 velocity change by A2 acceleration. Now I'm not being very thoughtful about time. I'm just thinking of one frame as one unit of time, so I'm going to do one adjustment to the angle. Whereas, if I'm really trying to be more accurate about this, I might try to do several iterations of the math per frame. That'll make more sense later as I get a little further here. But this should give me the structure from which to do this. So if I run this now, once again, it's not moving, but let's just give it a little bit of acceleration. 0.01. Let's make this one negative 0.001. Because now it's accelerating out of control really fast because those numbers are accumulating on each other. But you can see this is kind of the idea. I need to figure out what are those acceleration values of the angles. And if you go and watch my simple pendulum video, you'll see it's kind of an easy thing to calculate based on gravity. Really simple formula. The thing about the double pendulum is, and I'm not going to derive these formulas, but as I scroll through this page, it's going to actually attempt to derive those formulas of motion. I'm just going to scroll down and get to the end. Here we go. This is what I'm looking for. This what looks like double quotes is prime prime. So theta 1 prime is velocity, the angular velocity. Theta 1 prime prime is the angular acceleration. So all I need to do, no problem, I'm just going to implement these formulas in my code and we'll be done. Actually, why don't I just end this video right now? You do that. I'll be back later. OK, you're probably still here. Did you pause the video and do it yourself? This is going to be, so I'm going to, let's see, what's the best way for me to do this? What I'm going to do is, whoops, I'm in the wrong place, is I'm going to move this over here. I need a little more space. I'm going to actually just take a screenshot of this, absurdly, because I want to be able to see it and look at my code at the same time. So I should be able to go now to the, I don't need this open. I should be able to go to the desktop where I have that screenshot. And so I've got that up there now. And let's lower my processing window to down here. OK, so let's find a place where I can actually implement this. So I'll just do it at the top of draw. Theta 1, angle 1a equals. Now I just need to put all of that stuff in my code. So one time when I see like a formula like this, it's kind of like, I don't want to write this all in one line of code. It's going to be crazy. I like to break it up into parts. So first of all, there's definitely two parts. There's the numerator, which is the top of that, and the denominator. But there's also kind of parts of the numerator, because there's like this whole thing minus this whole thing minus this whole thing. So let me start doing it that way. Let me say float numerator 1 equals negative g. Do I have a variable called g? So g is the universal gravitational constant, I assume. That's just going to be 1, but we can play with that to change kind of like the strength of gravity. There's a real world number that is that I don't care about for the purpose of this video. So in a way, I want to like take it out, but I'm going to leave it in there. Negative g times 2, well, let's put parentheses, 2 times m1 plus m2 times sine of angle 1. So that's one thing. The next one is, and please, those of you live following along, tell me if I make a mistake here. The next one is negative m2 times g times sine of angle 1 minus 2 times angle 2. Then the third part here is negative 2 times sine angle 1 minus angle 2 times m2. Oh boy. Oh boy. Times, okay, let's make this, let's make the next thing m4, which is, oh, and this, so theta 2 prime is, in my notation, is angle 2 underscore v. I probably could have thought of a different name. So it's the velocity times r2 plus angle 1 underscore velocity. Oh, squared. This is squared too. Oh my goodness. So that's squared. So angle 2 velocity times itself, squared, times r2 plus angle 1 velocity times itself, times r1 times cosine of angle 1 minus angle 2. I think, and there's b parentheses around this whole thing, but since I made it its own thing, I don't have to. And then the denominator is r1, this is going to be a little easier, times 2 times m1 plus m2 minus m2 times cosine of 2 times angle 1 minus 2 times angle 2. Okay, so now, assuming I didn't make a mistake, which I'm sure I did, angle 1 acceleration equals numerator 1 plus numerator 2 plus numerator 3 times numerator 4. I think that's correct. That's all the, divided by denominator. And parentheses around all of this. Whew, okay. I mean, I almost want to just do that. Like, let's just run it with this and just say that angle 2 acceleration is 0. And by the way, this could be a local variable. There's no reason to have this be a global variable because it's going to get recalculated every frame. So let's take these out here and let's just see, like, syntax-wise, does this even run? Oh boy. Float angle 1. Oh, I forgot a semicolon. Okay, so this is promising. Why? Because that looks like a single pendulum. Now it's kind of spinning a little bit out of control. So like probably going to want to add some dampening, but this is right. It's going in a perfect circle. So I'm not totally insane. I've got something that's working here. That's kind of nice. Okay, now, time for formula number 2. And by the way, somebody in the chat asked what crazy person thought up this formula. Nobody crazy thought it up. Somebody crazy calculated it. And probably not so crazy. Somebody who's really very thoughtful and kind and really likes pendulums. And another video, I'm sure, could go through the math of this. But sometimes I like it when I'm like, oh, the coding train is not about deriving the math, just implementing it. So today is a day for that. Now I need to do, well, it's not going to let me redeclare these variables. So let's just use them again, whatever. Let's say 2 times sine of angle 1 minus angle 2 times, do I dare like keep going here? I'm going to dare keep going. No, let's do, the numerator 2 equals angle 1 velocity squared times r times m1 plus m2. Okay, that's 1. R1, that's R1? So easy to make a mistake here. Numerator 3 equals g times m1 plus m2 times cosine of angle 1, okay? Numerator 4 equals angle 1, where am I looking? No, angle 2 v squared times r2, 2 times m2 times cosine of angle 1 minus angle 2. And if I look here at this These are the same, right? The denominators are the same. The only thing that's different is L1 and L2. Double check, double check, double check, yes. So I could copy paste this code here and bring it down here and just say R2. Now, this now equals, right, it's numerator 1 times numerator 2 plus numerator 3 plus numerator 4 divided by denominator. Oh my God. What is the chance that this is actually correct? What is the chance that this is correct? Very, very, I'm being told that I have some transcription errors. Make it denominator 2. I did that. And A2A equals num1 times, okay, hold on. Let's look at A2A. Num1 times num2. Num1 times num2 plus num3 plus num4. I think that's fine. I think I'm good. Oh, there's a squiggly line here, yeah. Num4 is A2 squared times R2 times M2 times cosine of A1. I think I'm good. 34, I need a parentheses. I think I'm good. I'm going to run it. Huh. Does that look right? No. Okay, something's wrong. Something is definitely wrong. Okay, let's look at the let's look at the denominator. L2 times 2 times M1 plus M2 minus M2 times cosine of 2 times angle 1 minus 2 times angle 2. That looks correct. Okay. I'm seeing in the chat this. I think I need to be more thoughtful. Oh, there's a parentheses. Oh, this parentheses goes all the way to there. Oh, that's very wrong. Very, very wrong. Thank you. So this is this times all of that added together. So this parentheses needs to be here. There we go. I think now, no, not in denominator. In numerator 4. That's why. Okay. This, numerator 4. No, not in numerator 4. Ah! Oh, I was doing so well. It's in the end. This parentheses goes here. There we go, right? Because when I put this all together, I need this thing times these 3 things added together with parentheses around it. And if I want to be really safe about this, I'll put another parentheses around it. Okay, now. Okay. All right, hey, that looks kind of like a double pendulum. Whoa. Now, it's got quite a bounce to it. I don't know if I've actually done it right. It is kind of spiraling out of control, which I think maybe I might have an issue. So let's think about what could be the problem here. I don't think the order matters because putting it here is the same as, just not doing it the first frame. Oh, yeah. Well, yes, I should put, this is correct that this makes more sense to put here. Yeah, I think I actually have this correct. I think the issue is did that really just, weird. Did I do something that fixed it? Oh yeah, interesting. Oh, so that does matter. I was thinking that this doesn't really matter, but I definitely, the correct way to do it would be to adjust the velocity first based on the force, which is the acceleration, and then adjust the position. Somehow that seemed to have fixed it. There's also some, yeah. So, okay, so let's actually get it to do, so a couple things. One is I want to have previous x2 and previous x1. And what I want to do is I want to actually draw a line. I want to trace the line from previous x2, previous y2. Is that what I put here? Previous x2, previous y2. And I'm going to have these be, can I say that? No, can't have a float. So I'll just like set them equal to -1 or something. And so here what I want to do, as soon as I calculate this, I want to save. But I have to do it afterwards. I want to at the end, I want to save the previous y2. And I only want to draw the line if previous x2 is not equal to -1. This is probably a better way to like not draw that first line. Actually, I could just say if frame count is greater than 1. Okay, I just wanted to do that so I could at least draw the full path. So let's actually have it start. Let's do a couple things. Number one is let's have it start. Let's have a variable called center x and center y. And as soon as I set the size, let's say center x equals width divided by 2 and center y equals 50. That way I can reuse those, center x, center y, because I need that also here, center x, center y. I want to be able to see a bit more of the canvas, so I'm going to say like 900. Oops. Oh, and why is my background, width, this needs to be the same size, with height. Okay, this is a little bit better now. Now, let's actually have it start higher up. Let's have it start pi divided by 2, pi divided by 2. Let's see what happens here. So this should be, I think this is the right pattern. I don't know what initial settings to give it, but it kind of looks pretty similar to what I started with when I did that Google image search, right? If you remember my Google image search at the beginning of this video, this one, that looks pretty similar to that. So I think I have now done the double pendulum. Now, the thing is, playing with the mass, playing with the G value, playing with the different R values, playing with the color, there is so much that you could do with this. And I could also, one thing that I think might be worth just noting here, and I absolutely would like to also have this, I think I want to have a much lighter trace, right? So I have this. A couple things that might be worth noting here is that, what was I going to say? Oh yeah, I could add some dampening. So one thing I could do is say I could simulate this idea of like friction or air resistance by saying A1 times equals 0.999. So it's always losing a little angular velocity every frame. So we could do this. So this should, it might take a very long time, but this should eventually dampen those values so that it comes to a rest. So that's something to sort of play with. Certainly, just to show that effect really strongly, if I put like 0.9, if it's losing 10% of its, you can see that it's almost as if it's like swinging through mud. So that's one thing that we can kind of play with. I can't stop. And when this gets ported to P5.js as a JavaScript version, we can have sliders to play with all this stuff. But you can see what that really does. The dampening really causes it to not be able to swing. So I'm going to comment this out, though, and leave this in the code. The other thing that I would do is, what does it mean if the mass of these is 20? How does that affect the pattern that I'm going to get? What if I make the arm length of the first one like 50? Right? And the second one, like 400. You know, this is sort of interesting. What do I get? What kind of pattern do I get here? So there's so many possibilities. So this is the end of this coding challenge, the double pendulum colon challenge. This, I think, is one which is really ripe for your variations of, for your own, do your own twist on this. How are you drawing it? How are you visualizing it? How are you adding user interface controls? Is it the kind of thing that you make, how do you make it interactive? There's so many possibilities here. How are you drawing the trail? Oh, I gotta stop. So I hope you enjoyed this coding challenge. I would not be surprised, oh, more gravity, I'm being told. I could also change the force of gravity. Let me put this back up to something more reasonable. Right? If I make gravity really strong, you can see what kind of like craziness happens versus gravity really weak. You can see almost just more like this, almost imagine this double pendulum on the moon, so to speak. 3D version would be crazy. I can't make a 3D version. So I would love for you to make your variations of this. Share them with me. At thecodingtrain.com actually now has a system, a way for, it's not the most obvious thing, but it's tied to a GitHub repository where you can submit a pull request. Go check that out. There'll be a link in this video's description for how to do that. And I will also have a JavaScript version of this that runs in the browser, which the code will essentially look exactly the same. So thanks for watching, and I will see you in a future coding challenge.